thank you very much for the invitation and the opportunity to share our research conducted in Construct from the University of Porto. So I will talk about the experimental characterization of the structural behavior of masonry arch bridges and focus mainly experimental activities we conduct in our research group. So the objective is to identify material structural parameters of masonry arch bridges through laboratory and in situ testing to support structural modeling of bridges, of cases of bridges in operation in the Portuguese road and railway infrastructure. So the methodology is very similar to the previous presentations, particularly from Professor Carmelo, and it includes two components, one of experimental characterization and another of numerical modeling. For the experimental characterization, it includes the general characterization of the bridges, the geometric survey, visual inspections, and preliminary tasks. And for the experimental activities, material and structural characterization, including lab and in situ testing. With all this information, we use it to support updating and validation the numerical models, and then to perform structural analysis and structural assessment. So some words also related to the bridge models in the right-hand side. So we consider both FA and DA discrete models as well fan continuous models. We can see there are three cases for the same bridge. In all the cases, we consider a very detailed discretization of all the bridge components and materials. So a lot of parameters to be defined. And then the importance of the definition of model parameters based on experimental data and correlation between experimental and numerical results. So first, some words about the case studies, bridge from the Portuguese infrastructure. So they are all in granite stone. Here, two cases of railway bridges in the same line in the northern Portugal. Of about the same age. The first one, Dourange, with 16 arches. The second one with just one arch. It's a very common typology in our bridge, in our railway infrastructure. And also this large, also granite stone arch bridge with 8 arches. This one was built in 1944 to replace an existing metallic bridge with the principal arch with 20 meters span. And we developed also some studies in road bridges. So here are some cases. Lagoncinha and San Lázaro, they are both from the medieval period. The first one with 6 arches and the second one smaller with 2 arches. And finally, Vila Fria Bridge was constructed in 2007 using traditional techniques. We were involved doing research in this project. So, and it is about this type of constructions. We have some studies. So now going for the experimental campaign, starting for material characterization. The activities involve coring and sample collection. Here some locations on some cases of bridges, and all the samples collected related to stones, joints, and infill in these old bridges, and also samples from the material used in the constructions for the new bridge. So we should note that for the stone, similar materials, granite stone. Also for the old bridges, the joints are quite similar, mortared. But regarding the infill, we have quite difference from the railway structures to the road structures, with a cohesive material in the railway bridges and granular material for the road bridges. So going for the lab testing, we performed with samples of granite stone, the usual testing for this type of material, so allowing to obtain the elastic modulus, unit weight, compressive and tensile strength for all the samples collected. We can see here the range values we used then for performing our structural assessment. And with infill samples, considering the granular material, we perform also similar tests used for soils. So odometer test with samples collected from another bridge similar to the Lagoncina bridge, and allowing to obtain the elastic modulus. And using the materials used in the construction of the new Vila Fria bridge, we performed also triaxial tests with the pure granular material. We can see here the plotted in the plots the behavior recorded in triaxial tests. So allowing to evaluate the elastic models, but also parameters on the friction angle and the cohesion. With the joint samples, we performed shear and normal tests using a shear box machine. We can see in the figures. Allowing to obtain the normal and shear behavior of this type of interfaces. Here it is shown the behavior for stone-to-stone joints from samples collected from one case of one bridge. In this case, it is hard to take these samples to the lab, and the samples were already splitted during the transportation. Well, at that level, we perform also correlation with numerical modeling using the same strategies we use for simulation, the whole bridge model, allowing to somehow validate at a material level the parameters we are going to use. And we can see here the comparison between the experimental and numerical results with good correlation. Then in situ testing, flat checks and Menard pressure meter tests were performed in 2 cases of bridges, the locations. With the flat checks, we use 2 devices to perform double flat check testing. We can estimate the in situ deformability of masonry. We see there the plots of a cyclic test and the corresponding range values of the elastic modulus. For the in-field, in situ, we performed pressure meter testing using the previous scoring to insert the probe. You can see in the image, and the plots show the behavior recorded, and the estimations of the pressure meter modulus, which can be correlated to the elastic modulus of the materials. So also at that level, we conduct correlation with numerical simulation. Show there using a discrete strategy to simulate the flat check testing and the results, allowing the comparison between numerical and experimental behavior. For the pressure meter testing, also numerical modeling was conducted, and here using a continuous model, In all cases, at that stage, at that level, we can draw some conclusions related to the calibration of the material parameters to be used in global simulation of the structures. Then, going for global characterization of the structures, we conduct also model identification in almost all cases of the bridges we have studied. Here are some cases with the setup of the tests and the accelerometers placed on the deck. In case of that bridge at São Pedro da Torre, because it is much rigid, we have to use an additional device to produce more vibration on the bridge, but in the end we could obtain the experimental dynamic characteristics for all cases of these bridges. We can compare also here just the first frequency for the larger bridges with the smaller ones, and of course we have lower values of frequency for the large ones, and much better results for this type of constructions. Then the correlation of the experimental and numerical model parameters is for us an important step for validation, particularly the elastic parameters. I show here a comparison between experimental and numerical dynamic characteristics of one case. Ruben Silva will talk later more about this bridge. And also related to global characterization, load testing were performed, considering static and dynamic conditions, using the instrumentation to obtain the experimental behavior of the bridge response, and also allowing some comparisons with numerical modeling. Ruben will also explain more details on that. So, some conclusions. A general overview was provided concerning the use and real case application of experimental strategies for assessment stone masonry arch bridges. The cases highlight the potential of these experimental techniques and significant outcomes of the applied techniques, allowing better understanding material and structural behavior, and also supporting calibration of the bridge model parameters. A list of references on these cases, acknowledgement of the founding, and that's it. Thank you.